Hello everyone, it's Mr. Woodward. In this video I'm going to be talking about how to solve problems involving projectile motion when you have a projectile that's only being horizontally launched. So this is an introduction to horizontally launched projectiles. Let's take a look at the top here. Since projectiles have both horizontal and vertical motion, the big three kinematic equations can be used in both directions. In the vertical direction, projectiles are under the influence of gravity alone. So the vertical acceleration is negative 9.8 meters per second per second. In the horizontal direction, however, projectiles are not accelerating, right? Because gravity is not acting on them horizontally. So the horizontal acceleration is zero. So projectiles are just moving at constant velocity in the horizontal direction, but in the vertical direction, they're accelerating. So we're going to see how the big three kinematic equations can be applied in both directions. So let's start with horizontally. In the horizontal direction, the big three equations would look like this, right? Delta x equals v initial t plus 1/2 at squared. Equation 2 would look like this. Equation 3 looks like this. Okay? Now, I'm going to add some subscripts to show that these are horizontal measurements. So when I say v initial, I mean v initial x, right? These are in the horizontal direction. When I say acceleration, I mean acceleration in the x direction. Okay? And the final velocity is also just in the horizontal direction. Now, here's the note, right? The horizontal acceleration is zero. Projectiles are not accelerating horizontally, right? Gravity is not acting on them horizontally. So if this is true, this would apply here, here, and here, which means that these terms entirely go away, okay? That means that this equation right here, number 3, is just saying that the final velocity is equal to the initial velocity. That is explaining that the horizontal velocity is constant. So this equation doesn't really become particularly useful, right? This equation here, same thing, right? It's simplifying to final velocity in the horizontal direction is equal to the initial velocity in the horizontal direction. Again, that's just a restatement that it's going at constant velocity in the horizontal direction. So this one is also not particularly useful. And this first equation is the only useful equation in the horizontal direction. Okay? So I'm going to call this like equation 1. All right, let's look vertically now. We're going to have the big three again, but now I'm going to say delta y, v initial t, 1/2 at squared. Final velocity is the initial velocity plus the acceleration times time. And the third equation is now using the delta y, right? I'm going to go and add my subscripts. When I say initial velocity, I mean initial vertical velocity. When I say final velocity, I mean final vertical velocity. And when I say acceleration, I mean the acceleration in the vertical direction, okay? So that means this acceleration of negative 9.8 meters per second squared is going to apply here, here, and here, okay? Since the acceleration is not zero in the vertical direction, all of the vertical equations still apply and are still useful. So I can call this maybe equation 3, equation 2, equation 3, and equation 4. So we have one equation in the horizontal direction that's useful and 3 equations in the vertical direction that are useful. All right. Just gonna make some space here. Okay, so communicating, here we are here, communicating between horizontal and vertical directions can be done using the common variable of time. For example, if you use the vertical motion equations to calculate the projectile's hang time, This would be the amount of time that the projectile spends when it's in the air. You can carry this time over into the horizontal motion equation to solve for an unknown horizontal velocity or distance. Similarly, you may be able to use the horizontal motion equation to find the time and then carry that time into the vertical direction to solve for final vertical velocity or vertical distance, okay? So the way that we're going to communicate back and forth between these directions, the horizontal and the vertical, is through time, okay? Because time is not a horizontal or vertical thing. Time is a totally different dimension, but the time that you find maybe in the horizontal direction will be the same time as you apply in the vertical direction, okay? Projectiles will be moving with the same time in both directions. All right, so let's try an example of this, okay? Example 1, the greatest height from which a basketball has ever been successfully shot is 201.4 meters and was achieved by Derek Heron from the Australian show How Ridiculous at Malatsunaye Falls in Lesotho, which is a country in Africa, on January 13th, 2018. If Derek launched the ball horizontally at 6 meters per second, you can see that in the picture here, what was the range, meaning the horizontal distance of the shot when it landed? And then a couple notes, you may neglect the height of the basketball hoop above ground, because that would be, if it's actually shot, if it's hitting a basketball hoop down here, it would be quite short compared to the height from which the basketball was launched. So you can neglect the height of the basketball hoop. And then the other note is you may ignore air resistance. Air resistance would otherwise be significant at this height, but we're going to ignore that. All right, so we want to know this distance, okay, delta x. How far out does the ball land when it hits that basket? And we're given this distance, the height of 201.4 meters. Okay, so we're going to solve this problem in 2 steps. The first step is going to be to find the falling time, how much time the ball takes to hit the basket down here at the bottom. Okay, so step 1, I'm going to say find falling time. Now, to find the falling time, it is just going to be the amount of time that it takes to fall 201.4 meters. That's it. So let's use equation, what I'm calling up here equation 2, right? It's the first equation in the vertical direction. And the falling time is going to be based off of the height that it falls. Okay, these are, it's initial vertical velocity. This is vertical acceleration. Now, the ball in this case is just being pushed outwards, okay? It's not like it's rising up and then going down. It's only being launched horizontally. So the ball has no vertical velocity right off the bat, okay? We can say that the initial vertical velocity is 0. The ball is only being pushed horizontally. It's only being launched horizontally, okay? So this falling distance of 201.4 meters, I'm going to call that negative because the ball is moving down. The initial vertical velocity when Derek shoots the basketball is 0. He's just pushing it outwards. When I multiply that by time, that whole term goes away. And then the vertical acceleration, 9.8 meters per second squared, and then the time, okay? So the right side becomes negative 4.9 t squared. I'm going to divide both sides by that, take the square root, and the falling time is 6.41 seconds. That's how long it takes the ball to just fall from that height and hit the ground. Now I can take that time and figure out, okay, it's going to travel at 6 meters per second for 6.41 seconds. So now I'm going to go into the horizontal direction for my second step. I'm going to find the range. That's the horizontal distance that the ball travels, okay? And I'm going to use the first equation in the horizontal direction, okay? The range, the delta x, is going to be equal to that initial velocity multiplied by the time. So here we go. It's moving at 6 meters per second. That's how fast Derek pushes it outward from himself. And it's going to do that for 6.41 seconds before it hits the ground. So that means it's going to travel a horizontal distance of 38.46 meters. And by the way, that is approximately 126 feet by the time it hits the ground. Now, it would be very, very difficult for Derek to actually launch a basketball 126 feet. But since the ball is moving outwards for such a long time before it hits the ground, it allows the ball to travel 126 feet when it finally hits the ground. Let's move on to another example, example 2.